Hey pre-cal, and we are going to get started with section 7.3, partial fraction decomposition, and everybody needs to be sure they have paper out to take lots of notes here, and know that you can always come back to this video and give it another look. But this is going to be a lengthy section, and we're going to work through it piece by piece. So first of all, consider the word decomposition. So we are going to be taking apart something that has been composed, breaking down a rational expression into smaller, simpler, bite-sized pieces. That's what this section is all about. This section is essential knowledge for moving on to do calculus. Most especially, it's going to come up in Calc 2 when you are integrating with parts. We're essentially going to be reversing the process of getting a least common denominator. And that's why we spent a good amount of review time going over least common denominator in the previous homework. So we want to consider this problem. 3 over x minus 4 minus 2 over x plus 2. And if we get a common denominator here, that common denominator is going to be the product of x minus 4 times x plus 2. So normally when we're simplifying, our efforts are to condense and to get a single fraction using that LCD. And we need to be able to reverse this process. So, and like I said, that is for calculus. So this is what we did in the first homework assignment. We simplified using a common denominator. So that should be pretty nailed down at this point. So in calculus, you're going to need to integrate using parts rather than a whole. And what you'll find out in calculus is that an area of a curve captured in between an axis, x-axis or y-axis, or captured in between one slice of the domain. So it's easier to take the sum of all the parts and add them together rather than just to think in terms of the whole. It's the same thought process of the old adage, how do you eat an elephant? One small bite at a time. So we're going to be breaking large rational expressions into small bites. And I'm going to go over the process of how to do that. So we're going to consider 4 cases involving 4 different kinds of factors in the denominator. So yep, there's going to be 4 videos including this one. This video is dedicated to case number 1. Case number 1 is when we have a denominator that is a product of distinct linear factors. Distinct linear factors. All linear factors, which meaning a binomial factor and our variable is to the first power. Distinct linear factors. So this is our first example. 9x squared minus 9x plus 6 all over, and it's nicely already factored for us, 2x minus 1, x plus 2, and x minus 2. Now, first thing we're going to look for every single time is our rational expression, is it an improper fraction? And we get an improper fraction if the degree in the numerator is larger than the degree of the denominator. So this particular numerator has a degree of 2. This is a quadratic expression on the top. Now, if we were to multiply all 3 of these factors together, we would get a degree of 3. So, no, this is not an improper fraction. It's ready to go. If we have an improper fraction, that's going to be a different case that we'll have to look at. That'll add another layer onto the problem. So, the first thing we're going to do is we're going to break this down by the factors. So, there are infinitely many options as to what 3 different fractions could be to add together to get this. We could have 17 fractions that we could add together to get this, but we're going to look at a process that will systematically break it down and everybody will get the same thing. So if these are our 3 factors in the denominator, then we're going to put a variable expression a, and note the degree of that. The degree of that is 0. It has no variable expression. It's just the constant. So the constant a over 2x minus 1, the constant b over x plus 2, and the constant c over x minus 2. So this is the first step in breaking this or decomposing this partial fraction. Okay, so I've just recopied the same problem up at the top here. So we have same thing I just had on the second page. Our step 1 is to get an LCD and eliminate the denominators. Now, how can we just eliminate the denominators? Well, take a look at this card from when life was way, way easier. So why and how can we just dump a denominator? Well, let's consider this very, very simple equation. If we have x plus 3 over 7, and that's set equal to 6 over 7, as long as the denominators are equal, then we're comparing like parts. Therefore, if the denominators are the same, you can just dump them and you're done with them. And then all you have to do is solve the two numerator expressions set equal to each other. So that's why x has to be equal to 3. That's why in our problem, we can get a common denominator, and that will allow us to eliminate the denominators completely. So that's our step 1. Get the least common denominator and eliminate the denominators. Now, I've tried to keep everything color coordinated in this video. So if we have our given expression and we have a over 2x minus 1, then ask yourself, what is this fraction missing? This denominator is missing the x plus 2 and the x minus 2. So that a term needs to be multiplied by x plus 2 times x minus 2. That's what I've got here, the orange factor and the green factor. Next, b over x plus 2. What is x plus 2 missing? It's missing 2x minus 1, the yellow factor, and x minus 2, the green factor. So there's the yellow, there's the green, multiplied to the b. Finally, what's the c missing? Well, it's got x minus 2, so it's missing the yellow factor and the orange factor. So we multiply by orange and we multiply by yellow. Now, once we have established the common denominator all the way through the entire problem, guess what? We are now officially done with it. Goodbye, farewell, Felicia. So, step 2. Simplify the numerator using order of operations. Now, obviously with this much algebra going on, and I think I'll even take the opportunity to cover up some more of the problem just so it's not overwhelming. So if we're using order of operations, we've got to distribute the A, distribute the B, and distribute the C. And that's going to take us to this next step. Okay, so we used order of operations to distribute the A, distribute the B, distribute the C. And now we need to organize this information. So I've got our like terms color coordinated, and we're going to use the associative property and the distributive property to put together the terms that go together for the next step. That's step 3. Organize the right side. We're going to group the like terms together. So first of all, we've changed the order and got all the x squared terms together. Then we have x to the first power terms together, and then the constants together. Organize the right-hand side, group the like terms together. So once again, step 1, get an LCD and eliminate the denominators. Step 2, simplify the numerator while using order of operations. Step 3, organize the right-hand side and group the like terms together. So that was using the commutative property. Now we're going to use the associative property, and we are then going to set up a system of equations. So take a look at what I did. So I'll put that last step back up here so you can see it again. So there's step 3, organize the right-hand side. Now, notice what I did in the underlined orange here. Basically, I put all that together and then I took out the x squared and left in parentheses the quantity a plus 2b plus 2c. I did the same thing with the green scored terms. I took out the x. Be careful of that minus sign right there. Took out the x, and I'm left with negative 5b plus 3c. And then lastly, all the constants get grouped together. So now what we've got to do is we've got to compare using the definition of equality here and say, okay, if 9x squared minus 9x plus 6 is equal to all of that, well, by the definition of equality, which basically says that the left-hand side must weigh the same as the right-hand side, well, then what must be true? Well, if 9x squared must weigh the same as x squared times a plus 2b plus 2c, then 9 must be equal to a plus 2b plus 2c. And that's what you can see in this first equation. So if I cover up where I started modifying it, there's what's underlined in orange. Here's what's underlined in green. That negative 9 must be equal to negative 5b plus 3c. And then finally, the constant term on the left must be equivalent to the constant term on the right. And that is what you see here. That 6 is equal to negative 4a plus 2b minus 2c. So this is our system of equations, 3 equations. 9 equals a plus 2b plus 2c. Negative 9 equals negative 5b plus 3c, and 6 equals negative 4a plus 2b minus 2c. Well, step 6, we need to solve this system of equations. So that's what I've got here on the bottom of the sheet. So we're going to solve this system, and basically we just need to come up with a plan. Well, the first part of my plan is realizing that this second equation does not have an a term. And if this does not have an a term, it makes sense that we need to take the first equation and the third equation and eliminate the a's. That is why I have multiplied by 4. And when I multiply by 4, it brings me to this scenario. So 4 times 9 is 36, 4 times a, 4a, 4 times 2b, 8b, 4 times 2c, 8c. So when I transform the first equation into 36 equals 4a plus 8b plus 8c, I can compare it with this third equation, which I've written right underneath it, and I do a combination here, adding them together. The a's will cancel because 4a and negative 4a are going to have a sum of 0. So we end up with 36 plus 6 is 42, 8b plus 2b is 10b, 8c minus 2c is 6c. So that gives me my new equation, 42 equals 10b plus 6c. Now, just to make the numbers smaller, let's divide everything by 2. And yes, we can do that by the division property of equality, which gives us this handsome equation. 21 equals 5b plus 3c. Now, notice that I've got it circled in orange. I've got the middle one circled in orange because now this one does not have an a value and this one does not have an a value. And guess what? The b values have opposite coefficients. So those are the 2 equations that I am going to add together in order to make the b's cancel. So I add these two equations, the b's cancel, and I get 12 equals 6c, which means that c equals 2. So, if c equals 2, I'm then going to take that value for c and I'm going to plug it back into one of my modified equations that will then allow me to solve for b. And that happens just below. So 21 equals 5b plus 3 times c. c is 2. It gets plugged in right there. 21 equals 21 equals 5b plus 6. Subtract the 6 from both sides. 15 equals 5b. b is 3. Now we know b. Now we know c. We're going to take both of those values, the b value and the c value, and I chose this third equation that we really haven't even done much with yet, and I'm going to plug in the c value and the b value in there and there, which will allow me to solve for a. So now I know a, I know b, I know c. And if my initial directive was to decompose the partial fraction, I've done that because I've solved for A, I've solved for B, I've solved for C, and if you recall all the way back, this was our original breakdown: A over 2x minus 1, B over x plus 2, C over x minus 2. If I plug in those values back into that initial breakdown, this is my decomposed partial fraction. So I took the one large rational expression and I've broken it down into 3 bite-sized pieces. So that's what we would get. Now, just to give this a quick check so you can see how this works, we are going to add these 3 fractions back together. Negative 1 over 2x minus 1 plus 3 over x plus 2 plus 2 over x minus 2. We get a common denominator, which is just going to be multiplying everything back together. 2x minus 1, x plus 2, x minus 2. So the first term is missing x plus 2 times x minus 2. The second one is missing 2x minus 1, x minus 2. The third one is missing 2x minus 1 and an x plus 2. That away. Follow order of operations here. So I'm going to do the multiplication of all the binomial expressions first. So that's going to be negative 1 times x squared minus 4 plus 3 times 2x squared. So that's negative 4, negative 1, negative 5x plus 2. And then 2 times 2x squared positive 4, negative 1, plus 3x minus 2. Once again, all over that common denominator. And I'm just doing this check. These problems are not brief. They are long and arduous. I'm just using the distributive property now. Hopefully not making any careless mistake because I'm going fast. Okay. That's 9x. 9x squared. That's plus 6. That is negative 9x. Which, boys and girls, is what we started with. So, that is the first case when we have distinct linear factors. And I also want to point out there is another way to do this particular problem, and I have put it on the Google site. It's by using substitution and canceling out a couple of these factors. that it is simpler and it is shorter, but it only works when you have the simplest possible case here, which is why I wanted to show you how to use the system in order to do this. So please take a look at the other method that is given in the Google site, but we are going to have to use this particular method for most of our problems. You are awesome. Keep working, and I'll talk to you later.